For our example using Biot Savart, we're going to use a infinite wire that's carrying a current, infinitely straight wire, and we want to know what the magnetic field is outside away from the wire. Now we already know what the solution is, so hopefully we get to that solution. So let's start with our Biot Savart. Our differential is equal to mu naught I over 4 pi, and we have differential length cross r hat over r vector squared, distance squared. Now we can do this cross product in terms of the absolute values, and we know that this length is equal to dl vector times r hat times the sine of the angle theta that it makes. So this would be the length of this cross product. And this r hat is just equal to 1. It's just the length, right? And the differential length we're calling dy. So this leaves me with dy sine theta. And now I can rewrite my integral now that I've got my information. So B is equal to mu naught times the current divided by 4 pi, an integral from negative infinity to infinity of dy sine theta over r vector length squared. So now I have a problem because I have a sine theta. Theta is going to be changing as I integrate along this path. And then I have this differential y, and I need to get this in terms of one of those variables. So let's take a look at a trigonometric function, and I can say that y is equal to r over tangent theta. So y is just this distance that we're looking at from that differential length to the perpendicular. And if I take dy d theta, that's just going to be equal to r over sine theta squared. But sine theta squared is just equal to, if I have sine, then that's opposite. Here's my theta. So it's opposite. It's going to be r over the distance r, and that's going to be squared. And that gives me r squared, little r squared, over big R. So dy is equal to little r squared over r, big R, times d theta. And now I can put this into my integral. want to keep track that these were the limits for y because I've changed it now. I'm going to have r squared d theta over r, and then I'm going to have sine theta over little r squared, because that's just our distance, and that simplifies out. And now I'm going to change my limits of integration, and I'm going to be integrating along this length. So I'm going to be going from pi or 0 to pi radians. So it's going to be from 0 to pi. The r squareds are going to cancel out, the little r squareds, and I'm going to get sine theta d theta over big R. And now the R comes out because it's just a constant. And now I'm just going to do my integral. It's just negative cosine theta from pi to, or from 0 to pi. And I can now put in my limits. So I have a negative cosine of pi is -1. And then I'm going to have a plus, and cosine of 0 is 1. And that gives me, this is just 2 inside the parentheses, or the brackets. And that 2 is going to cancel out one of the 2's that's in the 4, and I get mu naught I over 2 pi r. So I got back to what I was originally using for the magnetic field due to a long infinite wire and the current flowing through it.